For the reaction stoichiometry moles and grams assignment, there are three types of questions that we'll see. Question 1 is a three-part question. It's going to ask us how much sodium azide is going to be used or produced as we do this decomposition reaction. So sodium azide decomposes to sodium and nitrogen in a 2 to 3 ratio. So for every 2 moles of sodium azide you have, you get 2 moles of sodium and 3 moles of nitrogen. Now question 1a is going to ask us how many moles of nitrogen are produced by the decomposition of 4 moles of NaN3. So that's pretty straightforward, right? We've been doing these for a long time. So let's take the 4.00 moles of NaN3 and we say that for every 2 moles of NaN3 we have 3 moles of N2. And since this is just a mole to mole conversion, we get 4 times 3 is 12 divided by 2 is 6.00 moles of N2 produced. Now it gets a little more complicated when we go down to part B, which is how many grams of sodium azide are needed to form 19.0 grams of nitrogen gas. So we're going to go from grams of N2 to moles of N2 to moles of sodium azide to grams of sodium azide. Okay. So as we go through and set this up, we'll start with the 19.0 grams of sodium. Use our conversion factors. It's 28.02 grams of nitrogen to 1 mole of nitrogen. And then for every 3 moles of nitrogen, you needed 2 moles of sodium azide. And every mole of sodium azide weighs 65.03 grams. So as we plug this into our calculator, we get 29.4 grams of sodium azide. Pretty straightforward calculations that we've done so far. But now we get down to the next calculation, and this is where things sort of go sideways a little bit. It's going to ask me how many grams of sodium azide are required to produce 15.0 cubic feet of nitrogen gas if the gas has a density of 1.24 grams per liter. Okay. So we need to go from volume of a gas to moles of the gas to moles of sodium azide to grams of sodium azide. And as we look at this, we're going to have a little bit more calculation to do. We're used to doing solution stoichiometry where we go from volume to moles using molarity, but we don't have that here. We need to convert volume to liters and then use density. So we'll start with the 15.0 cubic feet, and we'll convert from cubic feet to cubic inches. So for every 1 foot there's 12 inches, and we have to cube this factor in our calculator. And then we're going to go from 1 inch to 2.54 centimeters, and this has to be cubed as well. And then we say, okay, we memorize that 1 cubic centimeter equals 1 milliliter, and then there are 1,000 milliliters in 1 liter. And now we can finally use our density, 1.25 grams of N2 divided by 1 liter. Now, don't forget, it says 12 carat 3 and 2.54 carat 3 in order to cube these units for the conversion. It should come out to be 530.9 grams of N2 gas. If you do not cube the 12 and cube the 2.54, when you multiply them, this will be drastically smaller than what it should be. Okay, so next step. Let's take the 530.9 grams of N2 and go back up to what we did here in part B. Divide by 28.02 grams of N2 to get to 1 mole of N2, and then for every 3 moles of N2 we get 2 moles of sodium azide, and then for every 1 mole of sodium azide it weighs 65.03 grams, and when we plug this into our calculator we get 821 grams of sodium azide. So the trick in all these calculations is converting this volume here from cubic feet to milliliters, so then you can go to liters using density. Alright, now for question 2. Question 2 gives us the unbalanced equation. Iron 3 chloride plus silver 1 nitrate goes to silver 1 chloride and iron 3 nitrate. So before we do anything else with this, let's balance this real quick. If we balance it, we'll have 1 mole of FeCl3, 3 moles of silver nitrate, silver 1 nitrate, 3 moles of silver 1 chloride, and 1 mole of iron 3 nitrate. Okay, that's balanced. Now we can go through and do everything else. We have a 7.7, there should be a 0 here, gram sample of impure FeCl3 reacts with excess silver 1 nitrate. If the sample produces 6.24 grams of silver 1 chloride, what is the mass percent of iron 3 chloride in the sample? Okay. Mass percent, you'll recall, is the mass of the FeCl3 divided by the mass of the impure FeCl3 times 100%. We need to find this. In order to find this, we're going to take grams of AgCl, convert to moles of silver 1 chloride, convert that to moles of iron 3 chloride, and convert that to grams of iron 3 chloride. Okay, so we start with the 6.24 grams of silver 1 chloride. We're going to multiply that by the molar mass, which is 143.35 grams of silver 1 chloride per 1 mole of silver 1 chloride. And for every 3 moles of silver 1 chloride, we get 1 mole of iron 3 chloride. Okay, now we need to get to the mass of the iron 3 chloride. So we have 162.21 grams of FeCl3 gives me 1 mole of FeCl3. Plug and chug this into my calculator, I get 2.35 grams of FeCl3. My mass percent is going to be the 2.35 grams of FeCl3 divided by the 7.70 grams of impure FeCl3 times 100%, which comes out to be 30.5%. Okay, so if the question asks you to find the mass percent of a compound given an impure sample and giving a product. You can work the product back using the balanced equation to get the mass of the product, and then have the mass of the pure divided by the mass of the impure times 100% gives you the mass of the mass percent for this question. The third type of question here is going to be a little bit more laborious, so I'm going to dedicate its own video to this.